Okay, hello everybody. I hope that you can hear and see me. My name is Ralf Lehnert. I will give you now the lecture number 5 for the topic ICT in smart grids, or another word for this is smart grid communications. And today's topic is power line communications, transmission over the power line. My name is Ralf Lehnert. I was head of the chair of communication networks until 2014, nearly 5.5 years ago, and now the successor is Professor Frank Fitzek. Okay, so the topic is power line communications, using the power line for communication purposes. And I will follow this agenda. I give you a short introduction about the topic and a motivation why PLC is a good candidate for smart grid communications. I will give you some PLC systems ideas how this can be realized and specifics which is possible. And a major part of this lecture will focus on a standard which is now available for a couple of years, and in which all modern PLC systems are implemented because of its capabilities and also noise characteristics or noise hindrance characteristics. I will also present something about adaptive MAC layer switching. This is the idea of my former PhD student Stanislav Mudryevsky. He is the co-author of this presentation. I give you some conclusions finally, and in the end I will also give you a short presentation of a measurement tool to study the performance of real-life PLC systems in realistic applications. And of course, at the end you will find some references. So let's start now. Power line communications. Here you see some standard figures which you can find somewhere in the internet, in this case from an older version of PowerPoint. You are quite familiar with these high voltage lines. So you will find it everywhere in the world, in every country, and it is the so-called backbone of the power distribution network in every country. High voltage, the reason is quite simple. This means that the current on the line can be reduced, but in total you can have the transmission of very high power rates. So the backbone network usually has power levels from 110 kilovolts to nowadays even 500 kilovolts, and the most modern DC transmission systems go above of 1 megawatt. So here are some pictures to see how this looks like. Of course, this is only the a country's backbone network. In power transmission we have 3 hierarchy levels. This backbone level of high voltage lines. Then in a regional area, for instance in a bigger city or in a rural area, we have a so-called medium voltage distribution network, which is, at least in Germany, typically at a voltage level of 20,000 volts or 20 kilovolts. And finally, the lowest level is the distribution level, the access network, which how we call this in communications. The access network in power distribution networks is the low voltage level, and this is a voltage level of 230 volts single phase or 400 volts three phase. The three-phase network is very popular in many European countries, but there are also some bigger countries in the world, for instance also in the US, where we have a single voltage, low voltage network. So this is comes from tradition. Yeah, to use the power line for communications, we have to modulate data onto the power line, and doing this means you need a modulator, demodulator, a modem, which you perhaps know from your home access network to access the internet. And here is a picture which we took in Hanoi, Vietnam, where we studied our first PLC implementation network. And here you see this is a developing country, so the network architecture or the network hardware is, let's say, not as, let's say, standard as we may see this in Germany, but here are some of the modems just attached to the cable, and the data cabling is are the smaller cables here. So over this you have internet access, and you can go downstairs this pole, and there is the access to the in-house network in the nearby homes. Okay, so just to get a glimpse how it could look like in Germany, usually you don't see this implementation. The modems, they are usually in the power cabinet in your home, for instance. So, power line communications has quite a long history. In the early times, in the last century, it was used as a so-called carrier frequency transmission over the high voltage power lines. At that time, it was done in the modulation technique which people were able to handle with at that time. So it was a classical amplitude modulation, and a typically frequency for a power line transmission carrier was, for instance, 150 kilohertz. And as this is the switch gear of a high voltage network, it's difficult to see. So here these boxes are eventually the couplers where the transmitters were coupled onto the power line. This has been in use for quite a long time by the power utilities, the power providers, and they used the high voltage lines to modulate data onto it and to use this for internal company-wide telephony, for having a telephone connection from one of these switch gears in city A to the switch gear in city B, to eventually manipulate or maintain the high voltage transmission lines. So this is how it started. The idea to do this was even older, but the first implementation occurred in the 30s of the last century. This has been in use until recent times. So eventually, if you drive in a rural area and you have a radio in your car, and if you switch this to long wave reception, if you still have this kind of radio in your car, then you will, and you come by one of these high voltage lines which I showed you, you will hear a called humming noise, and these are eventually the carriers or the harmonics of the classical amplitude modulated carrier frequency transmission. This has been in use until recent years. Now we have glass fibers in the earth cable of the high voltage lines, and therefore we can use glass fiber communications. So it's dying out. It took quite a long time to develop more recent and more capable modulation techniques. Digital transmission and digital modulation techniques developed or were invented in the 70s, were started to be implemented in the 80s, and with the advent of modern mobile communication networks, we also use this for mobile communications. And that is why the integrated signal processing units became mass-produced systems, and therefore they became cheap. And that is why digital transmission started not earlier than in the 1990s, so about 30 years ago. It has been used for powerline communications from the beginning of this time in the 90s. So, for instance, one of the still existing home automation standard, KNX, KNX, still has a variant which uses PLC for transmission. In this case, it is so-called frequency shift keying. You have heard this in the communications, learned about this in the communications lecture. So, therefore, time was ripe for implementing more sophisticated powerline communications, digital powerline communications, and approximately in 1998 there was the first industry standard broadband PLC solutions on the market. So there were no longer existing companies, nor Web in UK, and another small company named Electricom, also in UK, and later companies in the US started to develop chips integrating the necessary signal processing capabilities and started their own PLC modem technology. Unfortunately, in the early days, the first 10 years of PLC, there were a couple of companies which of course were competitors, and they did not manage to agree on a standard. So we did have industry proprietary and completely incompatible solutions, and that unfortunately hindered the development of the market. But in the early 0 years of this century, standardization started, and in 2007 we had the first standard on broadband PLC, and 2 years later also on narrowband PLC. And also the standard which we will discuss today in a bit more in detail is the standard from the ITU, the International Telecommunications Union, and the standard is called G.HN. HN means home networking, although it is also suitable to be used in access networks. And this standard is very much interesting because it is versatile. It not only runs on the medium power line, it also runs over a TV cable, or on a fiber, or on a twisted pair cable. So all standard cabling we have, and therefore it can be used in different environments, and therefore it's now starting to become much more popular. Okay, so even if you did not hear about PLC in the past, you will easily understand that it is already in the world, it is existing. So for instance, if you have an electric car and you start to charge your car at one of these charging poles, then you use of course the cable to connect your car to the power outlet of this charging pole. And in order to identify the car, in order to identify what is the necessary voltage level and the necessary current level to charge the car appropriately, that the battery is charged and not discharged, and charged with the standard features which are allowed for that car, there is some communication. So if you switch your cable into both plugs on both sides, then there runs a short protocol identifying the car, identifying the capabilities of the car, and also identifying the maximum capabilities of the charging pole. And then the charging starts after you have authorized that you are allowed to take some power from this charging pole. The next step, and this is a step of especially for our topic of smart grid communications, in many households we do now have electronic meters, not the old-fashioned Ferraris meters which are running disk, and these meters are quite capable. They cannot only simply count the kilowatt hours you have consumed, they can also be bidirectional if you have a photovoltaic generation on your rooftop and so on. So they can provide a lot of information, minimum power used, maximum power used, time of the day information and so on. So you can do this metering, and of course to inform about actual values you do need a communications connection from your meter to your utility, and via your utility and the data base at the utility to your smartphone, that you can immediately read out what is going on in your home, even if you are not in your home. So the meter reading, or the smart metering, this is the buzzword, is the key to the success of the smart grid, because if we do know what is going on in the households, then we can provide, for instance, dynamic charging or dynamic tariffing. That means if it is a sunny day, as perhaps today, there is a lot of photovoltaic in the photovoltaic power produced, and therefore the kilowatt hour can be much cheaper than in winter times where it's foggy and cold, where you need much more power. So you can have dynamic pricing, and dynamic pricing allows you, if you do know what is currently the actual value of the kilowatt hour, to decide, okay, eventually I take my electric car and charge it now because the power is cheap. So this is the entry activity of the smart grid. I will come to further applications soon. Another application you may even use in your own home, that is LAN extension over Powerline. So if you have, for instance, computers in different rooms in your home, but you don't have the LAN cabling, then you can use the internal power outlets for connecting your computer with your router and with the internet, and you can connect or interconnect your home computers or your printer or what else you are using in your LAN, or do video streaming from your network attached stores, your NAS, in one room to the TV set in another room. That means you need a local area network with a significant bandwidth, and this is also possible, and that is called broadband PLC, or can be run with broadband PLC. Okay, to understand PLC, PLC means power line communications. So you usually have the power line. In this example, not very correctly, you see the power line on poles. There are power generators, for instance, these windmills, or the photovoltaic rooftop on your roof, the photovoltaic cells on your roof. And you are using power line communication. That means this is not only the power line to transfer electric power, but also the communications medium to transfer data packets, in Internet Protocol packets, IP packets, which are sketched here. Okay, the usual starting point of the smart grid is that you have at your utility a router and a server. To connect to the power line, you have a PLC modem which is attached to the power line, and via the power lines many homes are connected, not only private homes but also, for instance, industry buildings. And in your home you may have meters for electricity, for heating, for water, for gas. You must not have all of them, but at least you can have all of these. And that means, and you will in the future have intelligent power consumers. So for instance, the washing machine can become intelligent. In the most simple way, it can be remotely controlled when to switch on or to switch off, especially when the the kilowatt hour is cheap at a certain point in time. And that means you do need an internal communications with within your home network, or here is simply the modem, which has connections to the different meters, electricity and so on, and also to some of your intelligent devices in your home, and of course to interact with your photovoltaics. So in the case that there is a lot of sun, then please use this power to and eventually start the washing machine if you have filled it beforehand on the evening before, and you are out of home, but it is automatically started because now energy is cheap or even free of charge because you have produced it by yourself. So that means there are a lot of new opportunities if it is possible to either do remote metering and evaluate what you can do with the remote metering, and also take the information that there is the environment situation that that there is either photovoltaics, sun, or it's windy and the windmills can produce a lot of energy, and the windmills nearby to your home can do this, in order to avoid that we have only a centrally produced energy, which is the standard technology in the past and still until today. But as you perhaps have heard, in Germany we currently do have about 40% of renewable energy generation, and let's say 80% of this is from windmills and 20% is from photovoltaics. Photovoltaics currently growing faster than windmills. Okay, so to understand what does this mean for communication, the communication requirements in a smart grid. Okay, just to go back to this slide, if for instance you want to switch on the usage of your photovoltaic, or to control the usage of your photovoltaic, or to switch on or switch off your washing machine, or what else, the electric car to start charging, these are typically commands which do not have a very long length. A control command is typically addressing a certain device, so you do need an address, and you give a command on or off that is simply a binary. Well, usually you can do give some more information, start to charge your car with a certain energy and so on. So typically control traffic is a traffic type where the digital packets are small because they contain only address information and a very short control command. But if you want to switch something on or off, you usually do need a certain quite short delay. So for instance, if there is too much energy in the network and you have to switch off some of the producers, the energy producers, the photovoltaics, then this should be done in a short time, because otherwise the power network stability is in question. And of course, these commands have to reach the destination, so you do need a communication where there is an acknowledgement that your command has reached its destination. Usually, control traffic is not very high frequent traffic. This occurs, of course, with a short delay, but it occurs not too often. So the offered traffic load may be small. As all communication technology in such a network is in fact a computer, so a modem contains a certain firmware, or it contains data of tariffs and so on. So if one of these communications network devices has to be updated, then you have to update the firmware, and the firmware can be of a typical size of some megabits or megabytes. So in this case, it doesn't make sense to subdivide your information, your file for the firmware update in small packets. Then you usually use larger packets, and because here your requirement is to have quite a high throughput in megabits per second. The transmission time or even the retransmission time is not critical. If the update is not successful in this point in time, then eventually you can repeat this in the next night or whenever there is low important traffic load. So this means there may be some overload, so you have to establish the classical internet-based overload control mechanisms. Yeah, and I said one of the important usages is meter reading. Meter reading means, of course, at least in certain intervals you must be able to read out every meter. So that means all nodes must be reachable. That means you have the requirement that there is a very high availability of the nodes. It should be very near to 100%. Other critical requirements are not usually taken into account. Okay, so there are several communication transmission means or requirements, but the power line has a specific which is definitely critical and has to be accessed very carefully. The power line has been designed for transferring the electrical power. Electrical power transfer means that you have really physical lines. They can be thick lines for high currents. Therefore, the impedance is very low. It is typically the case that on a power network there are a lot of power consumers which are not continuously on, they are switched on and off. So there is a lot of impedance variation due to this fact that there will be a lot of changes all the time. Due to these changes, switching on a switch, you have some impulsive noise. This impulsive noise is directly related to the switch activity. In this case, it is asynchronous to the mains frequency of the power network, which is 50 Hertz in Germany, 60 Hertz in many other countries. And also there is some background noise. And we will discuss what kind of background noise is possible in the next slides. Also, we have to take into account that this is now a data communications network. And the data communications network has to transfer traffic which is varying. So the commands, the firmware updates, eventually also streaming information for some of the customers, manuals, and some advice how to install something in your home that not the technician has to visit you, and so on. So the traffic is, as in every data network, typically varying very much, statistical variations, time of the day variations, and so on. And we have different requirements for applications. As I mentioned already, commands must be acknowledged, and meter readings must be ensured, not within milliseconds, but over 24 hours. In each day, you must be able to read out a meter. This is one of the typical requirements. So that means fulfilling these requirements, we have the goal to optimally design the physical and the medium access layer for the current network conditions in a PLC network. Okay, how can we model a Powerline communications network? We consider only the access network, that is the network from the transformer, from the medium voltage to the low voltage network. This here is a symbol of the transformer. For communication purposes, this is also what we can call the base station. And typically, the wiring of the power cables from the transformer nearby your home is in certain trunks, and these trunks distribute typically in a tree-like fashion along the roads, and then you have short links to the home, to the house, and of course inside the house there is a similar fork type or tree type network. This this graph sketches only the distribution network from the transformer typical voltage to low voltage to the houses. And in a typical area, let's say not the most densely populated area in the city with high-rise buildings, let's assume that we have a suburb situation where there are individual private homes, then the distribution network may look like this. So there is some feeding cable, and there is, for instance, a small street with 3 houses. There are other streets, and there are these types of streets, and so on. And as a typical example, in Germany, for instance, and many other countries, one of these transformers typically feeds about 250 to 400 houses or subscribers. There are a number of sections or trunks, and per trunk there are typically these numbers of users or households or houses per section. Logically, the power line is a bus, a multi-access bus or a logical bus. That means we could also transform this topography into a logical topology where here the wide area communications network is connected inside the transformer compartment, and on the low voltage level there are many of these houses in having different distances from the transformer to each of these houses. So if we would have no signal attenuation on this link, we could deal this bus as a typical local area network with a length of, well, the typical length in a rural, in a suburb area is up to 500 or even 1000 meters. Typically it's shorter. So if the communication attenuation is small, then we can use the mechanics we are used to implement and to run in standard local area networks. So there is a strong similarity. Unfortunately, the attenuation along this link can be quite high because, again, the power line has not been made for communications purposes. So it is a low impedance link, but having quite a high attenuation for frequencies, for instance, in the megahertz range. And this is one of an example which Mr. Modrzejewski has used in his PhD dissertation. So this is an example, a power network, where here we have two transformers, here and here, access points where the transformers are located, and then we have feeding points, and the customers, the houses, are these EI, the typical standards. I should also explain that typically a power distribution network is designed such that in the case of a power outage, let's say a cable is broken, for instance, let's assume that this cable here is broken, then we cannot feed the typical way, but there is a connector or a switch at the end point, and if you close the switch, then you can feed the house here over this way from here. So typically the low voltage network in city and suburban areas is a ring which is usually open, but in the case of failure it is closing or even closing automatically, so there is no outage if we have just one link failure. And this is a typical example which we have been using in one of our research projects, and also it has been used by Mr. Modrzejewski. Okay, again the same situation. The transformer, the wide area access base station, and having, for instance, a first feeder link, then going further into this street, having a split connection, and going this street, there's another street, and so on. So in total, the distance from here to here is eventually a bit too long with respect to the signal attenuation of the high frequency signals on the power line. That is why we can use so-called repeaters. A repeater, well, as the word says, repeats the signal. In the case of power line communications, if we can receive the signal here and we want to retransmit it in this direction, this does not work, because the power line is a power line. The power line cannot distinguish between two directions. So if we want to feed in a signal here and we have received a signal from here, the signal must be transmitted in another range, either on the time domain or on the frequency domain. Here I assume that we are using frequency division multiple access. That means we have a frequency range of different types, modulation we will discuss later, a frequency F1, which is used only from the base station to the first repeater, and then we forward the repeated signal with frequency F2. In this case it feeds this street and it feeds this area until we eventually have a next repeater, and this next repeater goes to another frequency area F3, and for the most distant house we might even need another repeater. That means if we do use different frequencies, in this case 4. Our bandwidth which we can use is divided by 4 because we have 3 repeaters. F1 here, F2 here, F3 here, F4 here. If there is a strong attenuation, and definitely the attenuation from here to here over this long distance is eventually so strong that we can't hear the signal F1. We hear the signal F1 at this repeater only with a so low level that we can neglect it. So eventually we can reuse F1 for this last segment. And this is one of the design topics, which is of course also important in other communication networks, also in mobile communications. So the Powerline signal transmission characteristics are as follows. We do have quite a high attenuation for high frequency signals. Later at the end you will find references. For instance, there is a very recent book where there is a complete chapter on the attenuation topics of PLC signals. What we also have noise signals, and I will come to this soon. We also may have signal reflections, and definitely we have changing characteristic impedance. As I mentioned already, if you switch on and switch off power consumers, if you switch on a heating, then definitely the impedance goes lower, and if you switch it off, the impedance can go back to a higher value. And of course your communication system, the transmitter and the receiver, must be able to cope with this. Also there might be multipass propagation. So if we, as I said here, there are these so-called switches. These switches are usually open, but nevertheless you can understand this as a kind of small condensator. So there is some capacity, and high frequencies can be transferred via capacitors. That means that there might be some communication even over here, and that means there is a signal which is going this way, and there is a signal which is going over this way, and that is multipass, which we know very well and understand quite well from mobile communications. Also, frequency selective fading can occur. If there are signal reflections, this means that there are standing waves, and standing waves always produce frequency selective fading. And finally, due to a higher attenuation, you might have bit failures, bit error ratio. There is a so-called bit error ratio. Packets are a couple of bits, and in the end there might be losses of data packets, and we have to cope with this. So, to summarize, PLC transmission characteristics, a PLC network, the same one which I sketched already, can either be disturbed by power appliances, for instance any electronic system, a TV receiver for instance, or a washing machine, produces noise on the power line, produces impedance variations due to switching on and switching off these appliances, and the appliance can also produce high frequency noise. For instance, the fan in your hair dryer has typically quite a cheap electric motor, and this quite cheap electric motor produces a lot of brush fire, and that means this is noise, even high power noise. So one of these things running can disturb the performance of a PLC network. Also, there are radio transmitters, and if the radio transmitter transmits in an area where we do our modulation frequencies use on the power line, then this can disturb as well. The crane here is a high power consumer, again another consumer, and other PLC networks can disturb the behavior of a neighbor PLC network. So for PLC, the so-called electromagnetic compatibility is of prior importance. PLC systems, broadband PLC systems, may operate up to 85 megahertz. So they cover a range from 2 to 85 megahertz eventually. And in between there are a number of commercial or private frequency bands. For instance, the radio amateurs have their reserved shortwave frequency bands. There are other public radio frequency bands in it. So we have to take care of this, and I will show you how to do this. Also, the PLC networks produce their own radiation and can cause disturbances for other services, for instance, shortwave radio. And they may also be disturbed by high-power radio transmitters. In order that they do not produce too much own radiation, they usually work with a quite limited signal power. This also means that the PLC modems do not consume too much electric power. So the received signal is typically received in the noise floor of the background noise. That means we have to design these modems very carefully. Okay, how to deal with all these problems? What are the countermeasures? We have to use a very robust modulation scheme. And in the recent times there have been two developments triggered by the advent of modern mobile communications. One is the so-called spread spectrum technology, which for instance has been used in UMTS, the 3G mobile communications, and most modern systems now are running OFDM, orthogonal frequency division multiplex. These two mechanisms you have learned how they work in the communications lecture, so I don't have time to go into this. But what is important, as I showed you, the PLC network is a bus network. That means we have to organize the medium access. The so-called medium access control layer has to be designed carefully. Of course, the goal is to provide a maximum network utilization, but also we do need efficiency for all services, fairness for all services, and giving the quality of service for various services, different quality of service requirements for different services. So we must be able to do this, otherwise we won't have acceptance of the technology, and we must be able to be competitive with other access technologies in the world. And as usual in a communications network on a channel which may have errors, we have to install an error handling mechanism. So finally, some classification. PLC can be classified from the frequency bands used. The first implementations of PLC were broadband PLC networks, nowadays running the frequency band I mentioned already. They are usually designed for distances, smaller distances. Nowadays, I would say, from our experience and measurements we have done, even 1000 meters is nowadays possible. They have been more expensive in the past. Nowadays, the the integration in the chips has progressed a lot. So even they are not longer more expensive, and they can provide file layer speeds of nowadays even much more than 1 gigabit per second. On the other hand, narrowband PLC is designed in a very low frequency range, in a frequency range which is below the long wave radio transmission frequency. So the long wave range the long wave radio band starts at 150 kilohertz, and this is running below this. Due to the lower frequency, the attenuation is lower. That's why we were saying in the past we can cover longer distances, and we can do this at lower cost, at least with simple modulation schemes. The speed definitely is lower. For smart grids, as I mentioned already, at least for the commands, we do need a very low delay. And this is difficult to deal or to manage with narrowband PLC. We do need a high coverage. In this case, narrowband PLC has its advantages. We have to implement a low packet error ratio or a low packet error rate. Well, if we have enough speed, then we can implement this with higher redundancy. So this is perhaps better be done with broadband PLC. I skip more or less this complex slide. As I mentioned, standardization took quite a long time, and there are many proposals for technologies of PLC. In the end, most of them did vanish, and nowadays we have only few standards which are really of technical importance or implementational importance. For narrowband PLC, still Prime, this is a Spanish design, is existing because it's now part of the G3 standard. And in broadband PLC, we did have standardization. The first standard was IEEE 1901, and it is now superseded and extended by the ITU G.HN standard. And all modern systems now are running OFDM. One of the earlier systems here, for instance, the YITRAN implementation was running with spread spectrum techniques. So, again, I mentioned this already, this lecture focuses on access networks. So we are talking for smart grids on PLC in low voltage area, in low voltage networks. We are transferring data. We have the standard OSI ISO layer structure. This holds also for PLC. The only difference is that from the IP, nowadays IPv6 standard, to the network layer, in between there is typically an adaptation layer to adapt to some special requirements of PLC. The PLC network layer is a bit different from the network layer of a classical cabled, for instance, LAN architecture, and below as well. And but the architecture in principle is according to the OSI layer structure. Again, the example which we have seen already, and due to the kind how PLC developed, we have also a synonymous naming of PLC. A couple of promoters of PLC did mention or name it DLC distribution line communications. Well, because it is the access line on the low voltage area. So DLC and PLC means the same situation. So, for instance, if you have a bus, then you have, in this example, 6 nodes. The distance from the access node to node number 6 might be too long, that you have eventually to run a repeater. In this case, we have just one repeater. The node number 4 is also the repeater for node number 5 and node number 6, whereas nodes from 1 to 4 can be reached directly. Yeah, as I mentioned already, the Powerline communication channel is varying over time. Varying over time due to noise, to impedance changes and so on. That means if you have, let's say, 2, or in this case 3 wide area network, interconnections, access nodes. All of them are, let's say in brackets, are connected to the internet, but there might be failures. So this one might be disconnected for some time, the other one and the third one as well. And in this case, we must be able to do an automatic rerouting from the internet connection to these access nodes, that if, for instance, this connection fails, we must be able to feed via this way or via this way. And this has to be done automatically, and that means this must be implemented in a PLC system. Okay, so we have used already half of the time. I will make a short break here, and in the second half of this lecture we will focus a bit more on this count G.hn standard in order how to describe what are the topics and how can we implement it a high-performance PLC connection. Okay, thank you. Relax a moment and then we start with the second part of the lecture. Thanks.